please join me in welcoming to the stage Bennett Freck, the technical lead of LEAP Australia.
Thank you, everyone. So, digital mission engineering, what is it and why does it matter? Typically, when we talk digital mission engineering, we're talking about a single pervasive digital thread, a digital representation, physics accurate, of a real-world system of system. With how complex modern space missions are getting, it is critical that we are able to understand how these complex interconnected systems are going to function once they get into the real world. So having a digital thread that you can rely upon all the way from concept development through design and testing and into operations and sustainment is incredibly vital to the success of today and tomorrow's missions. But what does this all look like? Well, we can apply a building block approach to this. First, we look at, well, how do things move? Within the domains that we're interested in, whether that is air, land, sea, or space, or some combination of those, what platforms exist and how are they able to move within that space? From there, we look at, well, how do things interact? This is typically where we're talking about the payloads on each of those platforms. So what kind of sensors do we have? What kind of communication capabilities? Effectors, both kinetic and non-kinetic? Any EW or jamming? That's where these kind of questions come into play. And once these two layers come together, well, how are things used? In an operational sense, once all of these moving parts come together, how do we know that the system is going to complete the task it is designed for in the way we expect it to? With that in mind, let's look at an example scenario, one that is relevant to today's discussion just before me, and I'm sure a lot more discussion today and tomorrow. For a hypersonics hypothetical case, we first define the operational environment. Where in the world is this happening? Now, the beauty of a digital representation, one that mimics the real world, is we have access to any airspace in the world. Sure, we can recreate a test flight that we flew in Western Australia, but we can also mimic a hypothetical case in an airspace that we simply do not have access to in the real world, and we can better plan for those what-if scenarios. Again, we're able to model any craft. So we can model a real-world trajectory that happened and we want to recreate for further analysis, or we can model a hypothetical trajectory, a craft that we think we might have to counter in the near future. Any launch condition anywhere in the world, we're able to define that operational environment. Moving downstream, we can look at detection and tracking. So again, we're coming back to those payloads on each of our assets. Whether we have ground-based sensors, space-based sensors, whether we're looking at optical, infrared, radar, SAR, any of those questions we're able to evaluate here, as well as some of the challenges that each of those sensor types are typically faced with. So optical line of sight obstructions, jamming, countermeasures. We're able to explore not only what our sensors can see, but what information we can deduce about the launch that is happening. With that information, we move downstream again. We look at taking action, an intercept of that threat. Can we characterize the intent behind the launch? And do we need to take action? Now, all of this is really funneling down to two questions. Which of my assets is best positioned to take action? And is it actually capable? If we're modeling a certain threat, if we're planning for a certain contingency, do we have a countermeasure that is fit for purpose? And if our simulation reveals that it is not capable of reliably completing what we need it to do, well then what design changes do we need to make? How do we go about refining and iterating that solution for both current and emerging threats? So where does this get us? What analysis can we run? Essentially, any design variable in this massive design space is now open to our exploration. Satellite position, sensor specification, launch location, the number of threats launching. We can now change any of those design variables and immediately assess the downstream impact on everything else connected. What we see on the right-hand side here is an example of that. So an automated multi-parameter optimization study looking at a hypothetical launch, multiple threats at once, multiple cooperative assets as well, and we're optimizing position, location, sensor specification, all with a certain cost function in mind. Effectively, we are letting the software, letting the physics-accurate representation converge on a viable and optimal solution, considering everything from technical requirements to financial cost. Another front to all of this, and a benefit to having a digital thread for your real-world systems, is the need for synthetic data. We've heard today, and I'm sure it'll pop up more, about machine learning algorithms and the sheer amount of data in the real world when it comes to these modern systems. Whether you need to train human operators or whether you need to train machine learning algorithms, you require extensive, accurate, and dependable data sets. Again, the beauty of a digital representation is we can generate a synthetic data set for any sensor, any location, any event, and critically, we've got the truth data behind the simulated data as well, a key element to any machine learning efforts. So why does this all matter? Where does this get us? Again, I'm going to sound like a broken record given everyone who's come before me. We live in a rapidly changing ecosystem. That changing global environment is driving constantly changing program requirements. We've seen this with multiple high-profile cases in Australia and overseas, where everyone from SMEs to multinationals need to pivot seemingly overnight to a new set of requirements, a new threat, and a new set of system requirements. Ultimately, powerful market trends are driving solutions that need to be more and more complex, and yet they need to be delivered in less and less time. To combat this and to manage this change, we need to shift left. Engineering processes and space programs need to be able to put themselves in a position where they can make key informed design decisions earlier in the process. Now, the operative word here is informed. You need to have a physics-accurate model that you can depend upon and rely upon to make these decisions. Doing so is saving time, it's saving risk, it's lowering cost, it's allowing for faster program capture. It's benefiting all of the human stakeholders involved in these massive projects. And digital engineering provides the tools to do so. If we look at the space industry as a whole, we see how this digital transformation, this idea of a digital thread, is incredibly broad in its applicability. Everything from trajectory optimization to thermal management, 3D printing, conjunction analysis. The use cases persist from commercial applications through to defense and government projects. The James Webb Space Telescope is an example I particularly like, given the kind of multifaceted nature of that mission. It really reflects how critical a digital thread is from start to finish, and this is just for a single asset. Obviously, we're talking about one satellite here. We need to plan, we need to optimize a trajectory, one that is complex around the sun's L2 Lagrange point. We need to consider thermal analysis and the cyclic loading that all the components will go through, whether we go down the active or the passive cooling routes for thermal management. And when it comes to aligning that complex mirror, we need to make sure that is precise. It's calculated that throughout the James Webb Space Telescope, there are some 340 single-point failures. Instances where a single subsystem error would have likely spelled the incomplete deployment of that telescope. Again, that is one single telescope. Modern space missions, LEO constellations, UAV swarms, we're talking about so many systems that need to operate together in unison. Analyzing all of those what-if scenarios is simply not feasible without a digital representation to rely upon. So we've talked about the space industry here. It's worth noting that this building block approach, this idea of building up a digital thread, is applicable just as well to the air domain, to situational awareness, to the ground sector. The same process applies. Effectively, you build the physics-accurate representation of what you need, and the analysis that you're able to get out of it is dependent on that. A quick word to finish on LEAP Australia, and then I'll let you all get to your lunch. LEAP Australia fits into this in that we are the channel partner for ANSYS in Australia and New Zealand. Almost 30 years, we have a strong history in everything from fluid dynamics, structural analysis, electromagnetics, and of course this digital mission engineering solution. Hopefully, something I've shown today has piqued some interest for you. If you have any questions about how this digital mission engineering approach, this digital thread, can fit into your specific use case, then please come find myself and my colleagues after this. Be more than happy to chat. Thank you all for your time, and I hope you enjoy the rest of your conference.